All right. Good morning. Hello, class. Ah, welcome to day 2. All right, in quarantine here. Hope everybody's doing well. Saw that there's a few views on my video yesterday, so that's good. Keep up the good work. Hopefully, more people are watching. Today, we're going to be picking right back up where we left off. So, if you look right here on Canvas, all right. We just did day 6 yesterday, Maclaurin series, and today we're doing day 7, Taylor series. So it's the last day of this unit, and it'll wrap up, Unit 9A. And tomorrow I'm not going to post a video, but I am going to let you have a day to work on the review. All right, so you can kind of work on the review assignment there. If you click on the review assignment, you see it's just a practice sheet of everything we've done in this unit, as well as the answer key, so I would expect you to do that tomorrow. But today is all about doing day 7, Taylor series. So if we go here, as usual, there's the notes to print. Okay, this is what I'm going to be following along with right here, and what you can print off and follow along with if you like. Here they are already completed. Here's your worksheet as well as the answers, and then the video lesson is going to go right here as soon as I'm done. Okay, so let's go ahead and start, shall we? There we go. Aha! I'm getting the hang of this. This looks good. All right, so we got a little little warm up here, and it's not even really a warm up. It's more so just leading into today's lesson on Taylor series, centered at something other than 0. Okay, so what we learned yesterday was what a Maclaurin series is. Okay, so if we look right here, Maclaurin series just means that the center is at 0. Okay, so we're going to use the Maclaurin series in this particular example for the sine function. Okay, and determine how many terms. So we got to figure out how many terms we're going to need to establish an approximation for sine of 13. Now, if my function is sine of x and I'm doing sine of 13, that means x is equal to 13. Okay, so I'm wanting to figure out. No, that's ugly. There we go. I'm wanting to figure out what I have to the number of terms I'm going to need in my series. That if I want to approximate x equals 13 for sine of x, it's going to be within 3 decimal places. Okay, so well, first of all, just to kind of help us with this problem, okay, so sine of 13. If you do this in your calculator, all right, which I got it right here, it's 0.420167038. Okay, so that is the sine of 13. Now the whole point of a Maclaurin series or a Taylor series is to create a polynomial that can estimate points within the interval of convergence. Okay, so 13 is very far away from the center. So let's see how many terms we're actually going to need in order to make sure that it is within 3 decimal places. So to make sure that the approximation is within that amount right there. Okay. All right. Well, remember what it is for sine of x. Okay. So sine of x is equal to the summation n equals 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Okay, so I'm just doing I'm trying to figure out how many terms. Okay, what's my n value going to be that the summation to n equals 0 to some n value, I don't know what that is, of this function. So this is just my my Maclaurin polynomial. I'm trying to figure out how many terms I'm going to need. All right, that's going to make us within 3 decimal places of my actual answer. Okay. Now, this is kind of an opportunity for you to try to do this in your calculator. I got no math behind this right now. All I want you to do is test points. See what n value it's going to take. How many terms you're going to need that whenever I plug this into the calculator, all right, whenever I plug that into my summation on my calculator, like how many terms or what's the n value going to have to be to make this within 3 decimal places? Okay, I'll go ahead and save you some trouble, or if you've already tried on your own, you're going to need 20 terms. 20 terms, 20 long values that is going to be only within 3 decimal places. Okay, so that's not, I mean, that's cool and all, but I don't want to use 20 terms. There's got to be a better center that we can use to approximate sine of 13. Like right now the center's at 0, and that's not close at all to 13. Or yeah, not close to 0. Okay. So what would be a better center? Well, really, honestly, I mean, you have a lot of freedom with this. To kind of help us later on down the road, you want to pick a center that like you can easily compute for sine and cosine, especially if you're having to take the derivative and plug in the value and stuff. In this case, I'll just go ahead and tell you, you can say I will do like a center at 13, but I think a better center, something that we can actually compute by hand if we didn't have a calculator, a better center would be at x equals actually 4 pi, because that is like approximately 12.566, which is really close to 13. So if I make my center at 4 pi, which is an easy trig value to compute, the center is only off from the value I'm approximating by like 0.4 or something. Okay, so it's going to be a lot. You're going to need a lot less terms to approximate within 3 decimal places. So so let's say, okay, I got the summation n equals 0, and I'm trying to figure out how many terms I need of my new function. So the only thing that I changed, instead of the center at 0, is going to be at x minus 4 pi. So I changed the center to 4 pi, to the 2n plus 1 over 2n plus 1 factorial. So I can let you pause the video and again test this out and see what the n value is going to be. But if you were to test it, you get n equals, I got n equals 1. N equals 1, I get 0.4200 something something something. So I only needed really the 2 terms. So I needed 2 terms to be within 3 decimal places accurate, as opposed to 20 terms when my center was really far away. So that's the point of a Taylor series, is your center is no longer at 0. You're trying to pick a center that's closer to the point you're trying to approximate, so we need less terms to approximate it. So in this case, all I needed was n equals 0 and n equals 1. I needed 2 terms. So if I put a 1 right here, that's going to be within 3 decimal places. Does that make sense? So that is a that's really what a Taylor series is just being able to create a new center. So the math's all going to be the same. It's just about a new center. So let's keep going with it. All right, so just to kind of give a definition of what we just kind of came up with. So a Taylor series centered at a Taylor series centered at x equals a. So no longer is it x equals 0, it says equals a. The series is going to look very similar, but instead of zeros everywhere, it's going to be an a. So like if you look back from your notes yesterday, the series is going to expand to, instead of like f of 0, it's going to be f of a. Should just be a. I don't know where that extra line came from. But then plus, and then again the same thing as yesterday, but instead of f prime of 0, it's going to be f prime of a, and it's still over 1 factorial, so that's still the same. But then instead of times x to the first power, it's just going to be times x minus a to the first power. So all we're doing is including that horizontal shift. Okay, so we got a new center. The center's not at 0, it's at a. So plus f double prime of a, and then x minus a squared over 2 factorial. So you see the difference. This is no longer 0, it's just a. And then plus dot dot dot. All right, so what the pattern looks like, it's f to the n, it's still to the nth derivative, but instead of 0, it's a. All right, instead of x to the n, it's x minus a to the n, and it's still all over n factorial. Okay, so A Taylor polynomial of order or degree n centered at x equals a is given by p sub n of x equal to the summation n equals 0 to to infinity of f to the nth derivative of a times x minus a to the n over n factorial. So this is a Taylor series. It's called a Taylor series whenever you center it at something other than 0. Okay. So, makes sense. We good on that? Check. Smiley face. Okay. So there's your note slide for that. There's really the new stuff we're learning. We're gonna do some examples with this. And honestly, this lesson should be a lot shorter than yesterday's lesson. Okay. So we are going to find a Taylor series, okay, no longer centered at 0. It's going to be centered at x equals 2 for f of x equals x squared. I'm sorry, e to the x. Hold on one second. All right, cool. Yeah, so I noticed yesterday that a few times my content came into my camera. So I'm trying hard to kind of recognize that. So I'm trying not to come down to this point here. All right, cool. So anyway, all right, so we're finding a Taylor series centered at x equals 2 for e to the x. Now, e to the x is interesting because we actually know what the Maclaurin series looks like for that. We know that we've learned that yesterday and maybe even the day before that it's the summation n equals 0 to infinity of x to the n over n factorial. Okay. Now, the reason, so this is just the identity for centered at 0. Centered at 0. So if they ever talk about e to the x and the Maclaurin series for e to the x, you already know what that looks like. You should memorize that. Okay. If it's centered at anything other than 0, though, you're going to have to kind of go through the motions again and kind of recognize it. Okay. All right, so let's talk about what it looks like when it's centered at 0. Okay, and we're going to use it to the 3rd degree. Okay, to estimate the value of 2.1. So if I want to do that, just like before, I kind of want to consider what f of a is. In this case, it's 2, f prime of 2. Like yesterday, we were doing f of 0, f prime of 0. So f prime of 2, f double prime of 2, okay? And if we're going to the 3rd degree, might as well go to the 3rd derivative, so f triple prime of 2. Now, the cool thing is that the derivative of e to the x is always just going to be e to the x. So for all of these, it's just going to be e to the second, e to the second, e to the second, e to the second. Come on, there. No, that's just, I don't like that. Okay, so that's pretty cool. All right, and if I'm going to create the so I'm going to do the 3rd degree. So I'm going to do p3x is equal to. Okay, so it's my, if you look at the formula, it's my first term. So f of 2, which is just e squared. So I'm just going to write e squared plus, and then it's f prime of 2, okay, which is e squared, times x minus a, so that's x minus 2 to the 1st over 1 factorial. Okay, so just to get used to the formula here, plus, now f double prime of 2, which is e squared, times x minus 2 squared over 2 factorial. Okay. And so that's the second one, and we're actually going to the 3rd derivative. So we're going to f prime of 2, I'm sorry, which is still e squared, and then x minus 2 squared cubed over 3 factorial. So it's pretty similar to what it looks like when it's centered at 0. It's just that we now have a value on the top here. Here it's e squared, because usually it would be e to the 0, which is 1. That's why you see nothing at the top here. But when it's centered at anything other than 0, you're going to have to actually kind of write it out like I just did here. Okay. And I mean, I could simplify that down if you want to. I mean, if you really want to simplify it, you can maybe say that this is equal to, I don't know, e squared plus e squared times x minus 2 plus, how about e squared over 2 times x minus 2 squared plus e squared over 6 times x minus 2 cubed. All right. So I mean that's simplified enough. All right. So it wants me to use this polynomial that's now shifted to a center of 2 to estimate the value of e to the 2.1 power. Well, that's pretty nifty because 2.1 is really close to my new center, so it should be a pretty good accurate estimation of what that value is. So if I want to know what that value is, I'm going to do e to the 2.1 power in 4x. So e squared plus e squared times 2. Dang, I did it wrong again. Oh, no, sorry. I'm plugging 2.1 in for x instead of 2 or something. Yes, so 2.1 minus 2 plus e squared over 2 times 2.1 minus 2. So instead of plugging 2.1 into e to the x, I'm plugging 2.1 into the polynomial. Squared plus e squared over 6 times 2.1 minus 2 cubed. And that is approximately going to be equal to 8.166138,499, so on. And if you actually did e to the 2.1 power in your calculator, you get 8.166169913. So when we shifted the center to 2, and we really only did to like the 3rd degree, so that's only 4 terms, look how more accurate it is. It's still, that's what, a 4 decimal accuracy. Oh, and I just noticed I wrote in the dang video picture again. I apologize. Well, all that's saying is 4 decimal accuracy, and this value right here is just me plugging in 2.1 in for x. But anyway, if I plug 2.1 in for x, it's within 4 decimal places what the actual value is. So shifting the center is more accurate. All right. I'm actually doing pretty dang good. Let's keep going. All right. Find a Taylor polynomial of order 3. Okay, so order 3. Okay, order 3, which is pretty much just saying, I'm going to go to, hey, the 3rd derivative. Okay, I'm going to go to power of 3. And the Taylor polynomial we're going to create is for the function f of x equals 2x cubed plus x squared plus 3x minus 8, and it's centered at x equals 1. Okay, so we've actually never done a polynomial before. It's always been with like sine or cosine or something, so this will be good. So I'm going to f triple prime. So let's start by finding all our values at the center. So let's talk about finding like f of 1 first. All right, f of 1, if you plug that into the function, you get -2. F prime of 1, which is equal to doing like, so the derivative would be 6x squared plus 2x plus 3. And if I plug 1 into that, I got, y'all can check my math on this, but I got 11. If I did f double prime of 1, so that's going to be what, 12x plus 2. And if I plug 1 into that, I get 14. And we're going to the 3rd order, so I'm going to go over to the triple derivative, or the 3rd derivative. That's equal to just 12, and if I plug 1 into that, well, I just you get 12. And honestly, if I keep going, if I go to the fourth derivative or the fifth derivative or the sixth derivative, all the derivatives after this point are going to be equal to 0. So it's actually impossible to go or generate anything past order 3 because the values will always just go to 0. So this tailored polynomial, this is why we don't do it for polynomials often, because you can only make it so far. Okay. All right. Let's write it out. Let's write out the Taylor polynomial. Okay. So just kind of following along here, I'll write out the I'll write out the whole thing real fast. So like that'll be like f of 1, okay, plus f prime of 1 times x minus 1 over 1 factorial, plus f double prime of x minus 1 squared over 2 factorial, plus, and we're going all the way to the third degree, or the third term here, f triple prime of x minus 1 cubed over 3 factorial. So if I want to know, and that should be of 1 there and of 1 there. And so if I just got to plug in what those values are, which I found over here in red. So p of 3, I guess, of x, because we're going to the third term, is equal to -2 plus f prime of 1 was 11 times x minus 1, and that's over 1 factorial, which is just 1, plus f prime of, or f double prime of 1 was a 14, and 14 over 2, well, I'll write 14 over 2 x minus 1 squared, plus, and then f triple prime of 3 was 12, so I'm going to put 12 over 3 factorial is 6 times x minus 1 cubed. There you go. There is your Taylor polynomial of order 3, so third derivative, centered at 1. And you can simplify that further if you want. Like I know 14 over 2 is 7, and 12 over 6 is 2. So yeah, good job. It was nice. So Taylor, same thing as Maclaurin, only different center. Okay. Wow, I only got 2 more slides. Nice. We're at 22 minutes. We are doing good today, boys and girls. Okie dokie. So number 6. It says let f be the function that has the derivatives f of 2 equals 2, f prime of 2 equals -3, f double prime of 2 is equal to 16, f triple prime of 2 is equal to 5. So it looks like my center's at 2. Okay. And all the hard work really has been done. They found all the derivatives for you, so that's good. So I want to write a third order. Because we're given the third derivative. Taylor polynomial centered at x equals 2. Okay, so third order is p of 3 of x. Okay, and I'm just gonna go ahead and kind of like write it out with everything kind of solved in there. So like you can write out the whole thing if you want to, and then plug in the pieces. But remember, the first term is just f of a, or f of 2, which is 2, plus then it's f prime of 2, which is -3 times x minus your a value to the first over 1 factorial, which is just 1. And then plus f double prime, which is 16 times x minus 2 squared over 2 factorial, which I'll write 2 factorial. And then plus f triple prime of 2, which is 5 times x minus 2 squared over 3 factorial. Yay. So there you go. And because the center is at 2, then approximating the value 2.3 is going to be super easy. Okay. So let's do it. 2.3 is equal to, I'm just going to plug 2.3 in for x. So that's 2 minus 3 times 2.3 minus 2, which is just 0.3. Plus, I guess that's 8 times 2.3 minus 2 squared, plus, I guess that's 5, 6 if you did the factorial out. 2.3 minus 2 squared. And if you, and honestly, I mean, all I really care about is that you can create the Taylor series and you know to plug in the value, and then that value is approximately equal to 1.8425. So there you go. Again, using a different center to estimate points close to that center within the interval of convergence, if you will. Okay. So questions, comments, concerns on that? I can't answer those because I don't see you. Okay, so kind of piggybacking off of that, this sounds interesting. It says, this is something I want to point out. So beforehand, the one we just did, okay, so the problem we just did was a third degree or a third order polynomial. And now it wants me to write a second. It wants me to write a second order polynomial for the derivative centered at x equals 2 to estimate the value of f prime of 2.3. So what it wants me to do essentially is to take the derivative, okay, of the f equation, that's f prime, which is equal to the derivative of the polynomial I just came up with, and we did it to the degree of 3. Okay, so if we want to take the f prime, we got to take the derivative of the polynomial we just came up with that described it. That's all we're doing. And the reason it says second order instead of third order like before is because what happens when I take the derivative? What's going to happen to that constant? I'm going to lose it, right? And what's going to happen to that third derivative at the end, that power of 3? It's going to go to a power of 2. So that's why it goes. So when you take the derivative, it's actually going to shift from an order of 3 to an order of 2 because you're losing a power. Let me show you what I mean. So I'm taking the derivative. So essentially, I'm taking the derivative of what I came up with in the previous problem. What I came up with in the previous problem was 2 minus 3 times x minus 2 plus 8 times x minus 2 squared plus 5 sixths x minus 2 cubed. Okay. So if I take the derivative and get p prime of x, oops, and this was order 3. All right, so the derivative of 2 goes away. The derivative of this piece here is just going to be negative 3. The derivative of this piece here is going to be 16 times x minus 2, and then to the first power now. And then because in times the derivative of the inside is just 1, so chain rule doesn't matter there. And then plus, if I were to do power rule here, that would be what, 5 halves? Yeah, 5 halves x minus 2 squared, and then times the derivative of the inside. It's just that. So notice how it went from a power of 3 polynomial to a power of 2 polynomial. That's why we're talking about second order. Okay. So we found the Taylor series that described my function above, and now we're using that same approximation to approximate the derivative, all right, at 2.3. So now if I want to do p prime of order 3, which I guess in this case is 2, but that's fine, of 2.3, all right, that's just going to be equal to negative 3 plus 16 times 2.3 minus 3 to the first plus 5 halves times 2.3 minus, I don't know why I wrote 3 here, that should be a 2, minus 2 squared. And if you type that out in the calculator and simplify it out, it's 2.025. So there you go. We can also take, I mean, just like before, it's just taking the derivative of something that we came up with. So nice. All right, I'm under 30 minutes so far, and I'm about to go on to the very last example. So kind of cut the time in half from yesterday. It's because we already know essentially what a Taylor series is. We're just changing the center a little bit. Okay. All right, let's go out with a bang here. So, yeah. So, okay, we're writing a fifth order Taylor polynomial. So that's like to the fifth derivative. Okay. Centered at x equals, hold on 1 second. All right, cool. Perfect. Okay. Centered at x equals 2 pi over 3 for f of x equals cosine of x. So no longer is the center at 0. It's now at x equals 2 pi over 3. I know what the Maclaurin series looks like for cosine. That's something I would like for you to memorize. And just to kind of write it down here, yeah. Okay, just write down here. As the summation n equals 0 to infinity, if I can write clearly here, of -1 to the n times x to the 2n over 2n factorial. So that's what it looks like when it's centered at 0. But when it's centered at anything other than 0, okay, we're going to have to kind of go through the whole process again. So we're going to have to find the derivative up to the 5th derivative of x equals 2 pi over 3. So that's what I'm going to do now is I'm going to talk about what all the derivative values at the center, the new center now is instead of 0. So when we change the center, notice how it's not going to be canceling terms out. So this 2n is not going to apply anymore because 2 pi over 3, any form of it's never going to make the derivative or any derivatives equal to 0. So no terms are canceling out. Okay. So I'm trying to think of space-wise how I'm going to do this. Okay, I'll do it right. Here. So we'll do f of 2 pi over 3, which is equal to the cosine of 2 pi over 3, which is equal to -1/2. Cool. All right. Now, take you a second, and I'm just going to kind of like not talk here. I'm just going to write. I'm going to write all the derivative values up to the 5th derivative of the value 2 pi over 3. So you can check my math as you go. You can skip ahead of this part if you want, but I think it's helpful to write all this down. -√3 over 2 is the derivative value. The second derivative value is equal to negative cosine 2 pi over 3, which is equal to 1/2. Third derivative, 2 pi over 3 is equal to sine of 2 pi over 3, which is equal to positive √3 over 2. All right, the fourth derivative, 2 pi over 3, is equal to cosine of 2 pi over 3, which is equal to -1/2. And the last one is the fifth derivative of 2 pi over 3, which is equal to negative sine of 2 pi over 3, or negative √3 over 2. All right, cool. So I got down all the derivative values at my new center. And it wants me to write the 5th order, so I'm going to try to figure out space-wise. Let's see. I'll do it right here. I'll do P5 of x. And I might have to do this in 2 lines, but that's okay. All right, so it's going to be f of 2 pi over 3, which is -1/2. Okay. And then plus f prime of a, so that's going to be negative √3 over 2 times, all right, x minus 2 pi over 3, so x minus a over 1 factorial. Okay, so nothing too crazy there. And then plus f double prime, which in this case is plus 1/2 times x minus a, or 2 pi over 3, squared over 2 factorial. Okay, and then I'll try to fit one more right here, plus f triple prime of 3, which is root 3 over, root 3 over 2 times x minus 2 pi over 3 cubed all over 3 factorial. Nice, nice. Okay, and then plus the fourth derivative, so then plus, which I guess is going to turn to minus because that's negative 1/2. So it's going to be minus 1/2, okay, x minus my center again, to the fourth power over 4 factorial, okay, and then finally plus, which I guess is minus again because it is the fifth derivative is negative, so minus root 3 over 2 times x minus 2 pi over 3 to the fifth all over 5 factorial. Perfect. Okay. So there we have it. All right, we're going up to power, 0 power, power 1, power 2, power 3, power 4, power 5. And I'm good with this form of it. Okay, I mean, it is in the correct form. I never simplify down in the binomial. Okay, like that stays the same. Sometimes I will simplify down like the derivative value and the factorial on bottom. Like I would sometimes simplify, like the first term would be just like root 3 over 2 divided by 1 factorial. But like for instance, like right here, 1/2 over 2 factorial is like doing 1/2 divided by 2, or is 1/4. Sometimes I'll simplify that down. So if you want to do that now, you can. I'm not for this video. But if you want to simplify down those values, you can. Okay? Otherwise, that's the correct answer. So, yay, we did it. Okay. All right. Now, what it wants me to do in the next part is that I got the fifth order. It wants me to use that fifth order, which is centered at 2 pi over 3, to estimate to estimate 2.3. Okay. Now, the center's at 2 pi over 3, which is like 6 point something divided by 3. So it's the center is around 2.3 itself. Okay. So using to the fifth order should be a really, really accurate estimation of what cosine of 2.3 actually is. So if I want to do that, for the fifth order, I'm doing 2.3 is equal to, okay, it's the same problem that we just came up with, okay, but instead of x, we're going to have 2.3. So I almost am tempted to not write out that thing again, but I guess I will. Negative 1/2 minus root 3 over 2 times, now 2.3 minus 2 pi over 3, okay, plus 1/2 2.3 minus 2 pi over 3 squared over 2 factorial, plus root 3 over 2 times 2.3 minus 2 pi over 3 squared all over 3 factorial. Wait, that should be cubed, I'm sorry. And then plus, or minus, it should be minus, I'm sorry, minus 1/2 2.3 minus 2 pi over 3 to the fourth over 4 factorial, and then minus root 3 over 2 times 2.3 minus 2 pi over 3 to the fifth over 5 factorial. All right, which is approximately negative 0.666, oh that's lovely, 2760764, okay, which if you actually did the cosine of 2.3 in your calculator, you'd get negative 0.666, that's accurate, 2760213. Look at how close that approximation is, because the center was so close to the value we were approximating. And we went all the way to the fifth order. That's really far away down the list. Okay, so that's a 1, 2, 3, 4, 5, 6, 7 decimal accuracy. Okay. All right. Well, that is all of these slides that I have for this lesson. So 20 minutes less than the video from yesterday, so that's pretty good. Can't find my mouse. Let's see, there it is. Yep, we are done. So good job, class. If you have any questions, please reach out to me on Remind app. There is a worksheet as well as some practice problems to try. And if you have any questions on those, please ask me. And then tomorrow is going to be your day to review this. And then, so tomorrow is your day to review this. That is going to be, what's tomorrow? Wednesday? No, Thursday. And then we'll talk about what's on Friday after that. Okay? All right. Well, hello. Hello. Did y'all see that yet? Hello. Hello. Goodbye. All right, I'll see y'all.